Okay, so we got the General Lee jumping the riverbed. For that jump, this information is known. The General Lee is launched at 32 meters per second, 20 degrees above the horizontal. Okay? We want to figure out the distance across the river and the maximum height that General Lee would achieve from this jump. Okay, so on Friday we looked at like the mega whoosh thing, right? The guy that launched himself supposedly across that impossible distance and landed in the kiddie pool. This is the same thing. We have a projectile that is launched at an angle. The angle happens to be 20 degrees above the horizontal, and we know that the projected velocity is 32 meters per second. Okay, so what we need to recognize is that the General Lee is going to follow a projectile arc, like anything else that's launched at an angle. Okay? And you can see that in all the jumps we watched, every single time, that's exactly what it did. It went up and back down in this nice projectile arc. Okay? Objects can't help but do that unless they have wings. Okay? And then they can, or they're CG, and then they can do magical things, which we also saw. All right. So what we have to remember is that there's a vertical component to this motion that undergoes accelerated motion due to gravity, and there's a horizontal component to this motion where the object travels at a constant velocity. Okay. So horizontally, we're always using v equals d over t. Vertically, we're dealing with accelerated motion, so we know that the acceleration is negative 9.81 meters per second squared, but we might use any one of the acceleration formulas here. All right, so on Friday we talked about how this is our projected velocity, okay, and it's 20 degrees. Our horizontal velocity, which is constant, will be the horizontal component of that. Okay, we know it's moving 32 meters per second at 20 degrees above the horizontal, so that's got a horizontal component and a vertical component. Okay, the horizontal component we can calculate using trigonometry, so cos of 20 times 32. All right, so General Lee is moving horizontally at 30.07 meters per second as it flies through the air. Okay, that's all we know horizontally right now. What we're trying to calculate is how far it is across the riverbed. That would be the horizontal distance. What do I need? I need time. All right, so now I can look at my vertical information and see if maybe I've got enough vertical information to calculate the time. So in the same way that the horizontal component was my horizontal velocity, the vertical component of this number is my initial vertical velocity, because this is what the General Lee is doing at time 0. Okay? We know that vertically the velocity is going to change because gravity is going to accelerate the object. Okay? But I can still calculate what my initial velocity is using trigonometry. So sine of 20 times 32. Okay, so we got 10.94 meters per second. So the General Lee is moving vertically at 10.94 meters per second up on its initial launch. Okay, that's fast. But it's going to accelerate at 9.81 meters per second squared, so it's not going to fly very far. Well, far enough. Clears the riverbed. Okay. So on Friday, what did we say we have to remember about an object that's launched at an angle in terms of its vertical movement? Okay, goes up, comes back down. Right, VF is the same magnitude as VI, but in the opposite direction. Now, that's only true if the object takes off and lands at the same height. And basically, we just assume that that's the case in most cases. Okay? It's not impossible to do a projectile motion question where that's not the case, but in this case, this is easier. Okay, so I've got A, VI, and VF. Can I find T? Right, so T will equal VF minus VI over A. So negative 10.94 minus 10.94 divided by negative 9.81. I'm just going to multiply the answer by 2 because that's what negative 10.94 minus 10.94 is. I'm going to divide that by 9.81. So the General E is going to have a flight time of 2.23 seconds. It's a long time to be in the air. Okay. Right. This number is the only number that can be used by both the horizontal and vertical components. So now I can calculate D. So 30.07 times 2.23 . Okay, so the distance across the riverbed, the distance this car flies through the air is 67 meters. To give you an idea, that's 2/3 of the length of one of the straightaways on the running track out back. Like exactly 2/3. Okay, so imagine jumping from the end down there by that building, okay, to past where the gate is by probably another 10 meters. Flying through the air, okay, in a car. Right, it's a long way, okay, and they actually did this jump, but of course no car would survive, okay, a landing like that. Now, here's the reason it wouldn't survive the landing. The height it reaches. Okay? This isn't just the horizontal part. Okay, yeah, it travels 67 meters through the air, but it comes crashing down because of gravity. So what we want to figure out as well, and what the question asks is, how high above it does the General E fly? So what it's asking us for is what is our maximum vertical displacement? Okay, can I still use some of these numbers? Which ones?
Acceleration.
I can still use acceleration.
The initial vertical velocity.
And the initial vertical velocity. Okay? I can sort of use the time, but not all of it. How much of it can I use? Half. Yeah, okay? I mean, the maximum height occurs halfway through its flight. So I'd be able to use the time provided I divided it by 2. I don't recommend that. Here's why. Nobody ever remembers to divide it by 2. Okay? So there's actually a way to do this, okay, that doesn't involve using the time you just calculated. If I throw this pen up in the air, how fast is it going at its maximum height? 0. So we just got another number. And we didn't have to calculate it. So I've got VI, I've got VF, I've got A, and I'm looking for D. Do I have a formula that can do that in one step? Which formula should I use? VF, VI, A, and D. Right, this one. Okay, this will allow me to calculate the maximum height of the General E, okay, without time. So I just need to manipulate for D. So I'm going to subtract VI squared over to the other side. And then divide by 2A. So that that's going to be 0 squared minus 10.94 squared divided by 2 times negative 9.81. Okay, so 0 minus 10.9. Well, actually, I should use the whole number. That's terrible. I was just about to not do that. Okay, so the general A reaches a maximum height of 6.1 meters. That's roughly the equivalent of dropping it off the top of the gym. And now that only makes it go vertically. Remember, it's also moving horizontally at 30 meters per second when it crashes into the ground. So there's the whole falling from 6.1 meters and the whole traveling at 30 meters per second. It's pretty hard on cars. They're really not designed for that. Okay? And remember that this is also pre-airbags. You could never do this show now. Because every time they jump, the airbags would go off. Well, it's pretty hard to drive when that thing blows up in your face. Anyone ever had one go off in the face? It's really loud. Okay? It's like 120 decibels because it's an explosion. The only way you inflate that bag, okay, so quickly is by having an explosion happen that inflates the bag. Yeah. Okay? So, yeah, you'd never be able to replicate this with like a modern car. There's too many safety devices to save your life. That would get in the way. All right, everybody kind of follow how that works? That is like the stereotypical projectile motion question / I'll put it on the test later.
And how many significant digits did
I think I only had 2, right? Yeah, 32 and 20, yeah, just 2. Okay. Now, I'm going to show you another video. This one of like terrible, terrible movie physics. Okay. Do you recall, remember we talked about the suspension of disbelief? Yeah, this is a movie where don't watch it. It's 2 hours of your life you never get back. It's complete and total waste. Okay. So initially, what we have, okay, is this cannonball being fired at 40 degrees above the horizontal at 140 meters per second. So they're telling us, okay, magnitude and direction of the projected velocity. A very common mistake here is to try and use that 140 as either vertical or horizontal. It isn't, okay? It's 40 degrees above the horizontal. So there's a horizontal component and a vertical component, and the cannonball is going to do this, just like any other projectile, right? Unless you're told otherwise, assume that the landing point and the launching point are the same altitude or their level. So what we have to remember, once again, is that this side here, the horizontal component, will be our horizontal velocity. And this side here will be our initial vertical velocity. Right? So when you're filling stuff in here, obviously our acceleration is negative 9.81 meters per second squared. Okay, and the rest of it we have to calculate. Right, so how would I calculate V horizontal? What trig function am I going to use to calculate V horizontal? Cosine, yeah. Okay, so we got cos of 40, okay, times 140. All right, so it's 107 meters per second horizontally. Okay, I'll keep all the decimals in the calculator. And then I have to do the same thing vertically. That'll be the sine of 40 times 140. Okay, so 89.99. meters per second, and that's going to be up. And what's VF going to be? 89.99 meters per second down. Okay? Unless you're told otherwise, you can assume that that's true. Okay? If there's a difference in the launch height and the landing height, then it's not true. Okay? But if you're not told otherwise, we assume that they're equal.
Later on, are we going to learn how to do it if they're at different heights? Or-
Yes, but I never test it. Okay? All that changes really is you've got VI, and then you'll know your vertical displacement, because it won't be the same, right? Like, they won't be the same height, so you'll have vertical displacement instead of VF. Which just means you use a different formula, and you can get VF, you can get T, or whatever, right? It just works differently, because you have a different set of information. All right, so we've got, okay, define time, VF minus VI over A, so that'll be negative 89 minus 89 divided by negative 9.81. All right, so the cannonball's in the air for 18 seconds. So it was launched from pretty far away. So we got our time, 18 seconds. That we can bring over here, and now we can calculate the horizontal distance traveled. And this is what somebody in artillery would have to do. Okay, if they were going to launch a cannonball or a shell at a distant target, they have to figure out what angle do I put the artillery at, and how much powder do I use to get the velocity, the muzzle velocity I need. Okay, so we've got our 18 seconds. Okay, so V times T, we take our two numbers there. All right, it's going to travel almost 2 kilometers. In fact, I think we only have 2 significant digits, so it's 2.0 times 10 to the 3 meters. Okay. It's a long way. Okay. Modern artillery can be launched much further than that. All right, questions on that one? What else do I have to calculate? Yeah, the vertical displacement. Okay, I just calculated the horizontal displacement, right? But now I got to calculate its maximum height. Right? What I have to remember is that there, VF is 0 meters per second, which means that I can then go that D equals VF squared minus VI squared over 2A. Okay? And so we'll have 0 minus squared divided by negative 19.62, which is 2 times 9.81. All right, reaches a maximum height of 412 meters. Also very high. All right, is there another way to calculate that maximum height? There is. Okay, remember we said I have to remember VF is 0 and that how much of the time has elapsed at that point? Half. That means I could also use this formula. Have the acceleration, I would know this is half of the time I calculated. Whoops, sorry, that's not 0. I can't cancel that out, but that's okay. Okay, I can use that formula, okay, plus 1/2 AT squared, okay, and just go 89.9 times, what was half my time here? It was 18 something, 18 seconds, so is it 9.15, say. Okay, I have to remember to do that. I have to remember to divide it by 2. I have to remember to make the 9.81 negative, right? Or this works out really weird. Right, so I'm going to have to figure out what this is divided by 2. Okay, so divided by 2. All right, so now I've got my half the time. Okay, I'm going to take my 89.9 times that, okay, plus 0.5 times negative 9.81 times that number again, but squared. And I get exactly the same number, which I should. Okay? We're talking about the same motion and I'm using the same numbers. Okay, how are we feeling about those launched at an angle ones? Okay, there's different ways I can ask those, but this is kind of the typical way that they might work out. All right, I'm going to throw something at you and see if you remember how to do this. These are the ones we talked about before. Projected horizontally, so there's no trig. Okay, these are just right off the cliff horizontally. Give you a few minutes on that one and see if you can remember how to do it. All right, so on this one, we've got a horizontally projected projectile. Okay, the person is running off at 8 meters per second. Okay, and we know that we're looking for the height of the cliff. So we're looking for the vertical displacement. Okay, we know the initial vertical velocity is 0 meters per second. Okay, we know the acceleration is 9.81 meters per second squared downwards, right? And horizontally, we know that the speed is 8 meters per second, and we know that the distance is 15 meters. Okay. If I'm going to calculate the height of the cliff, what do I need? Time or VF? There's no way for me to get VF, so I'm going to get time instead. Okay. So can I find time with this information here? Yeah. So I'm just going to manipulate V equals D over T. So it'll be T equals D over V, 15 over 8. All right, so we got 1.875 seconds as our time. That can come over here to the vertical parts. And now I can calculate D using this formula. It's the one we use every single time, it seems. Okay, that's going to be 0, 1/2 times 9.81 times 1.875 squared. All right, so the cliff's 17 meters tall. Okay, actually, it's 2 times 10 to the 1 meters tall, because it only has one significant digit because of the 8.
So, wait, in this situation, when you move the decimal, it would be 1.7 times 10 to the 1, wouldn't it?
Only have one significant
Oh,
digit.
wait, yes.
That's why. So it's 2 times 10 to the 1. Okay, questions on how that one worked? So we remember how those go.
Since it's displacement, would you want it possible to calculate? Or are you doing distance?
Well, I'm just calculating the height of the cliff, which would be more like distance. I could say down. That would be how far I traveled. The question's worded so it's height of the cliff, which would be more of a scalar quantity, but if you wrote down, that's also how you traveled, and I would accept that as correct answer. Okay. Okay, so here's a little bit different one. It's projected at an angle, so back to what we were doing today, but now it wants you to calculate the angle. Gives you a very different set of data this time. Okay. Now people really get thrown by this, but there's actually very little to do here. Like, this is a much shorter question than the ones we've been working on, if you figure out how to do it. All right, so on this one, we've got our projected here. We know that this number is 35 meters per second. We don't know what that angle is. But we do know, horizontally, the time, which can actually be both, okay, and it's 2.5 seconds. And we know the distance, 70 meters. What can I calculate with those two numbers? The horizontal velocity, which represents another side of that triangle. If I have two sides, can I find the angle? Okay, so you got to do 1 v equals d over t calculation. So we got 70 divided by 15, and we got 4.67 there. Okay. All right, now that I know that, and I know that, it's going to be a steep angle, right? This is a very small number compared to that one. By 2.5, not 15. It's not going to be quite a steep angle. Right. That's a better number. 28. Okay. So now that we've got that, now we can calculate theta. I have the adjacent side and the hypotenuse. So to get theta, I'm going to go cos to the -1 of adjacent divided by hypotenuse, right? And that should give me my answer. Okay, so it was projected at a 37-degree angle. Again, like one like that seems like it's like confusing and it should be a lot of work, but there were literally 2 calculations to finish that one off. Okay, way less than a typical projectile motion problem. I once put that on a test. It didn't go well. People thought it was too easy that way and tried to do it other ways. Like I actually saw people's writing this and they're like, well, that can't be right. And they tried other stuff that was wrong. Okay, never doubt it. Okay, if you're confident in what you're doing, okay, go for it. All right, this one's even more different. This one really requires thinking because it gives you virtually nothing. And you have to have a really good understanding of how the vertical part of projectile motion works. Okay, in order to get this one. We are looking for the projected velocity here. Right? All we know is the rock is thrown into the air. We don't know the angle, we don't know the magnitude. And that's what we want to find, both of those things. And all we know is that it travels horizontally 30 meters in 10 seconds. All right. There's a bit of an algebra trick to this, I'll tell you that. Okay, I'm not going to do it all, just going to give you another tip here. If I'm going to find the hypotenuse and this angle, I need both. This side, which is pretty easy to get, and this side, which requires a little algebra. It's a bit of a trick. I will remind you that this object is launched from and lands at the same altitude. That tells you something about VI and VF. Give you another couple minutes before I do. So I've got time and acceleration. I need to get VI. That means I probably also need VF, right? The VI and VF are the same number. They're opposite in signage, but they're the same number. So here's the algebra trick. In that formula, VF and VI are the same number. So I can just say this, A equals negative V minus V over T. They're the same number, but opposite signage. And that's what I've shown here. That now says that A equals negative 2 times V over T. Now I only have to solve for one variable because it's the same magnitude for both VI and VF. Okay, that's the algebra trick. Okay, since VF and VI are equal, I can set it up like this and solve for V and have the number I'm missing in order to get the hypotenuse and the angle. Okay, I am gonna post a quiz after school today. It'll be on projectile motion, but like the standard stuff, nothing like this that's crazy. Okay?